Hi all, this is Amelia. Welcome to Heat and Mass Transfer. Today we're going to be doing problem 5.41. So we're given, we've got a schematic down here, but we've got some number, doesn't really much matter, of stone concrete slabs. They're in this chamber, and onto them we're blowing a bunch of hot air from a solar collector. Um, and so we're using these concrete slabs to absorb thermal energy from the air. We're going to heat them during the day and then release the heat at night. So this is just kind of a standard thermal engineering type of thing. The intake, the incoming air during the daytime, that T infinity and H, we're going to have 200 degrees Celsius at 35 watts per meter squared Kelvin. And we're going to assume that the initial temperature of the concrete is 40 degrees Celsius. So we want to find the slab thickness, 2L. So actually L would be, half this thickness. You can actually see that here, 2L. Required to transfer total amount of energy such that 90% of that total energy is transferred over an 8-hour period. So we're going to assume, we know it's a transient system because it's changing with time, but we're going to assume the properties are constant and don't change with temperature. We're going to assume there's no phase change. So for example, if your concrete is sublimating, that's generally bad. We're going to assume the air is dry, so we're not going to deal with any kind of water vapor like latent heat or anything like that. So quality of life assumptions. We're also going to assume, because it's a convective system and we're going to ignore radiation, that our BO number is represented by H times the characteristic length divided by the thermal conductivity. So here's our system. If you want to pause here, go ahead. Our solution, we've got this stone mixed concrete. Here's the numbers for it. I lifted them out of the back of the book. I'm sure you can find the table, but we've got mass density of 2,300 kilograms per meter cubed, thermal conductivity of 1.4 watts per meter Kelvin, and CP of 880 joules per kilogram Kelvin. We've got our BO number, and our characteristic length again is 2L, which is the thickness of the slab, divided by 2 because it's from the center line, and that's L. We're going to start with lump capacitance. It's probably not going to work, and actually we'll find out later that it doesn't, but who knows? We might get lucky. And if you do it this way and it turns out great, great, problem done, quality of life. So we've got this Q of t divided by Q max is equal to this 1 minus e to the negative t over tau. And Q max is given here. It's it's again MCP delta t. It's that whole thing. We've got our theta I is our initial temperature difference between the slab and the air. And we've got our time constant rho LC CP over H. If we calculate our time constant, that comes out to about 5.78 times 10 to the fourth L seconds. Remember, that's seconds, so it's going to take a while. And our time that we actually want this in is 8 hours times 60 minutes per hour times 60 seconds per minute, just converting this to seconds. And it's 2.88 times 10 to the fourth seconds. So we've got our T over tau, which is 0.498. There should be an L there. Whoops, my bad. So we've got this Q of T final over Q max, again, is 0.9, which is what we want. We're looking for that 90% mark, as was stated up here. We're looking for the 90% mark is equal to 1 minus e to the negative 0.498 over L. Sorry, that should be over L. Again, my bad. It comes from dividing T by tau. Now, if we do that, we get 0.1, we just do the math, 0.1, move the 1 over, do some natural log stuff, divide out the negatives, blah, blah, blah. We get an L of 0.216 meters. But that's an answer. Like, sure, it's an answer, but we should check the BO number just to make sure, just sanity check, right? Make sure we're not doing something stupid. And look, it didn't work. Our BO number is at least an order of magnitude greater than 0.1. So no, lump capacitance don't work for this. Don't do it. Then we're going to assume 8 hours is a pretty long time. Like the time scale, Fourier number, it depends on like so many things. We're just going to assume this. If it works out, Great. If it doesn't, we'll fix it later. Quality of life. So we're going to assume Fourier is greater than 0.2. We know that Fourier is alpha t over LC squared, which is kt over rho CP LC squared. For conduction in a plane wall, LC is equal to L. So we're still good on that part. And we're just going to see what L approximately do we need if we want a Fourier number greater than 0.2. So we do our KT over rho CP LC squared, plug in all the numbers, make sure your units cancel. If they don't, something's wrong. And we're going to get Fourier number has to be at least 0.02 over L squared. If you use that same 0.2 and you divide stuff around, you will end up with a kind of a guess of a BO number. You don't have to do this. This is just me spitballing of about 7.8. Again, this is not this bit right here with the nominal BO number, not real math. That's just a place to start. It's like, should I look at BO number of like 1 or should I look at BO number of 500? Well, I'd rather not check every number between 1 and 500. So give me a ballpark, right? So because we're assuming Fourier number is greater than 0.2, we're going to immediately jump to first term approximation. Don't get me wrong, I don't like BVPs as much as anyone. So what we're going to do here is going to do our theta star of x star Fourier is going to be this first term approximation, where theta naught star is going to be constant 1 times e to the negative lambda 1 squared Fourier. We also recall that theta star is the non-dimensional temperature gradient or temperature delta T, sorry. And so that's time or temperature at some position time minus the conduction divided by your maximum delta T. But remember also that Q is proportional to delta T because Q is mCp delta T. And we are also assuming that density and all the other stuff, because M is just rho times density times volume. We're assuming nothing ever changes. All the stuff is the same. So we can say that Q over Q naught is the same as MCP delta T at whatever time divided by max delta T. And if you cancel out the MCPs, this looks all awful lot like this. So we're going to get what we're looking for is when theta star is equal to 0.9. We should also mention here that x star is x divided by the characteristic length, which varies from 0 at the center line to 1 at the surface. So let's pick a BO number. Just, again, swag it. Sorry, that's a work term that I will not mention. That it's not what it's not. It's not the colloquial slang version. Anyway, pick a BO number less than 7.89. So we try a BO number of 7, and we find from table 5.1 again. I like BVP as much as anyone, except BVP props. So go to the tables, use your tables. Don't be a mathematician, be an engineer. Get your constants, get your lambdas, figure out theta naught star is equal to this. But we also remember two things. One, theta star is equal to theta naught star times this cosine function. But since Fourier is 0.2, we're not dealing with just surface stuff. This is not semi-infinite solid. Well, we're assuming it's not semi-infinite solid. So we need to pick x star such that the whole block is at least at the minimum temperature. Because we don't want it to, we don't like, if you had, this big concrete slab and you blasted it with radiation for like 10 seconds, sure, the top inch or whatever is going to be extremely hot, but deeper in, it could be, it's, okay. If you ever had shirts, or I'm borrowing a steak example here, where if you put your cold steak on hot pan, the outside will crisp and the inside will not know that it's getting cooked. So same deal here. We're not blasting this with radiation. We're washing hot air over it for like a zillion hours straight. So we would like to pick an x star such that the whole block is at least at the minimum temperature. And that actually ends up being 0 because we're like, what's x star at 0? That's the center line. So if the center is at least at that temperature, we're good. That's FDA recommended. Um, so that means cosine of 0 is 1. We're good on that end. Cancel out the cosine. Don't deal with it. So what this ends up meaning is that our theta star is equal to our theta naught star is equal to 0.9. Now, take those numbers from the table, plug them in, do the math, some natural logs, some stuff cancels out. We get L, which is again not the whole thickness, just half the thickness, but it's stepping stone. We get L of 0.3383 meters and Fourier of 0.175. That's not quite 0.2. So we got to try again. Like this is kind of an iterative process, much easier if you have a computer. If you're doing it by hand, this is iterative process. So if we do a BO number of 5, which is about the same as our with the results that we got earlier from our pumped capacitance, is about 5. Let's try that. I mean, maybe it'll be closer. So if we do that, again, go to the table, get your constants, do the math. Should be pretty easy. We end up with Fourier number of 0.185, which is closer. Can we get closer? It's relatively easy at this point. We're not doing any kind of crazy math. Use the table. Try BO of 3. This is still greater than 0.2. Get a C of 1.2, a lambda of 1.2-ish. Ballpark it. Do our math. We get a 2L of 0.618 meters and a Fourier number of 0.208, which is greater than 0.2. So smiley face. We're good. That's our answer. All right. Thank you.